All right, so I want to kind of sum up what we were just talking about with radiation, or actually give another example. So we were looking at blacktop versus cement here, but think about when it's in the summer and here it gets pretty dang hot. When it's in the summer, if you're wearing like a black t-shirt versus a white t-shirt or a lighter t-shirt, okay, which one makes you heat up faster? It's going to be the black one, right? So when you're wearing the black t-shirt around, it gets hot fast, okay? Especially when you're like directly in the sun, okay? And that's because black is more effective than white. White will reflect back those colors, and so you won't retain as much heat, okay? So it sounds like, it would be better to have the white, but when we're talking about heat transfer, black is more effective, okay? Okay, so when we're talking about radiation, there's this law that comes up, and it's called the Stefan-Boltzmann law of radiation, okay? It describes the rate of heat transfer emitted or by emitted radiation, okay? So it says Q over T equals sigma, or the Stefan-Boltzmann constant, and it's given here, times E, or the emissivity of the object, or the measure of how well the object radiates. So for an example, an ideal black body has E equals 1, and a perfect reflector has E equals 0. Okay, so that's like what I was talking about with black coloring versus the white coloring. The black will, it's called, well, if it is ideal, it'll be an ideal black body, it'll absorb everything, and then your perfect reflector would be a lighter color like white. Okay, it's trying to reflect those things. Or the heat, okay? Times A, or the surface area of the object, and times T to the fourth. And that is going to be the absolute temperature in Kelvin. Okay? So, when we're looking at the net heat, or the net rate of heat transfer by radiation, it's going to have a very similar equation, but now we have some difference in temperature. Okay, so this is going to be T2 to the fourth minus T1 to the fourth. Okay, so I wanted to note a couple of things. When T2 is greater than T1, the value here, this rate of heat transfer, is positive. Okay, so when this is positive, this value here, the net heat transfer is from hot to cold. Okay, now when T2 is less than T1, then that means that this would be negative, and the net heat transfer is from cold to hot. Okay, but when we're looking at nature, okay, we know that heat transfer, so heat transfer is from hot to cold. Okay, so we won't really need to worry about this much, but maybe if you do get a negative answer, then you say, hey, wait a minute, maybe I set it up wrong. Okay, all right, so let's go ahead and finish off with our last example, 14.9. Okay, it asks, what is the rate of heat transfer by radiation with an unclothed person standing in a dark room whose ambient temperature is 22 degrees Celsius. The person has a normal skin temperature of 33 degrees Celsius and a surface area of 1.5 meters squared. The emissivity of the skin is 0.97 in the infrared, where the radiation takes place. Okay, so what we're going to do is we're going to use that equation that we just learned. Q over T equals sigma E A times T2 to the fourth minus T1 to the fourth. Okay, and remember, we want to set this up properly. Okay, so T2 is going to be the hotter temperature, or actually, wait a minute. This is going to be the cooler surrounding temperature. So this is 22 degrees Celsius. T1 is going to be 33 degrees Celsius. And remember, we want this to be in Kelvin. So to translate that, we'll just add 273. 273, whoops. And that'll give us 295 Kelvin and 306 Kelvin. Okay. All right. Let's see what else. We have our area. We have our emissivity. Should be good to go. So we have Q over T equals our Stefan Boltzmann constant, which we have defined as 5.67 times 10 to the negative 8th joules per second meters squared Kelvin, times our emissivity, which is 0.97, times our area, which is 1.5 meters squared, times T2, 295 Kelvin to the fourth, minus 306 Kelvin to the fourth. Okay? So, doing this calculation, putting it all into your calculator, you will get negative 98.5 joules per second. Okay, and with that, I did kind of falsely mention a minute ago, and I'll go back over this, that Q over T in this case is negative. Now, this negative is telling me that heat is flowing out of the system. Okay, so heat is flowing out of the system. Okay, so if this was positive, heat would be flowing into the system. Okay, so let me do this. Okay, let's see. Let me erase the pen. Again, okay, so it's not that it's from cold to hot. Okay, so this net heat transfer is going to be flowing out of the system. Okay, so this must mean that it's the heat will be flowing into the system. Okay. All right. So hopefully that makes sense, and I kind of cleared it up. Okay. So again, in this case, we found the rate of heat transfer by radiation, and the room is 22 degrees Celsius, and the person is at 33 degrees Celsius on the surface. So this person is then losing heat. Okay, so that's what we found. Heat is flowing out of the person's skin. Okay? All right. One last thing that I wanted to touch on is the greenhouse effect, and this is due to radiation. Okay, so when we have the sun giving off visible light, UV lights, and so forth, okay, it is putting that or shining, okay, these waves travel to the Earth, and then the atmosphere is able to trap some of those waves. So the atmosphere is able to trap the infrared waves, okay? And so what happens is they kind of reflect off of Earth and then hit the atmosphere and reflect back, okay? So this is how we are able, or not we, but the Earth is able to warm the surface, okay? Again, it's trapping this energy into the atmosphere, and this is a natural phenomenon. It's occurred here since we've had an atmosphere, okay? And it provides suitable life for Earth, okay? These temperatures are suitable for life, okay? So this is something that's very important. This also happens on another planet, I believe, Venus, that this happens on. So Venus has a very high temperature because it also has its atmosphere is able to trap a lot of this energy. Okay, so this is just the last thing I wanted to talk about. And I will have all of this stuff up very soon. And I will see you guys next time.